Welcome. Thank you for being here with us. So our speaker today is Dr. Roger Myers, and he's worked on in-space transportation, propulsion, and power for over 35 years, having worked at the NASA Glenn Research Center and held various executive positions at Aerojet Rocketdyne. He currently advises multiple clients on space mission design, propulsion, and power system technology and flight system development, business and program management, and employee development. He's worked on dozens of successful commercial, civil, and defense space missions and R&D programs in chemical, electric, and nuclear propulsion and power technology, and has over 100 publications in his field, including co-authoring the recent report titled Weighing the Future: Strategic Options for U.S. Space Nuclear Leadership, which is widely credited with guiding NASA's current space nuclear program. He served on several National Academy of Sciences committees, including co-chairing the Committee on Space Nuclear Propulsion for Human Mars Exploration, and currently serves as the chair for the NASA Space Technology Industry Government University Roundtable. Dr. Myers was elected to the National Academy of Engineering in 2022, elected Fellow of the American Institute of Aeronautics and Astronautics in 2010, and elected to the Washington State Academy of Sciences in 2012. And in addition to all that, he's a great friend and supporter of the Museum of Flight and is one of our trustees. We're super excited to have him here today. Please welcome to the Museum of Flight, Dr. Roger Myers.
As I usually do, but we're here to talk about something that's been in the news a fair amount in the last year, which is putting nuclear reactors on the moon. And more generally, how do we develop space nuclear technology? What are the first steps? The report that I co-authored last year was really to look at the national policies that would enable the United States to establish a leadership role in nuclear space systems. The first step is nuclear power plants on the moon. And so what we're going to talk about today is why are we even talking about it, and how are we going to do it? And it's a broad audience. Some of you are, I happen to know, nuclear technology experts, and some of you are completely new and you just came in. So I'm going to hopefully be able to keep all of you a little bit interested in this. We'll geek out a little bit. And then we'll also just talk in more general terms about the technologies and what we need to do in order to make this happen. So what are we going to talk about? We're going to start with why. Why are we going back to the moon? What's important? What are we trying to accomplish? What are the requirements? And one of the key differences here are that we're trying to go back for a sustained presence. It's not just flags and footprints like we did with Apollo. We'll talk more about that later, but it's fundamentally different in this time than it was back in 1969 through 72 when the first Apollo missions. We're trying to go back we're trying to establish a sustained American presence on the surface of the moon. What does that mean? What are the lunar environment constraints? What are the options for power systems? Why is nuclear power the right answer for a sustained presence for these current objectives? Then we'll talk, some of this is going to be a little technical. We're going to talk about space nuclear power systems, the subsystems that it will take and what the status is of each of them, how they work a little bit. And then we're going to talk about how we can build on those technologies to extend to Mars and nuclear propulsion systems. Just a very little bit on those two topics. And then I'll just very briefly get you up to date on what's happening today with the status and plans with NASA's programs, but also some commercial activities that are happening. So it's actually a very exciting time in this. So those last topics are about how. So the why and how. So why are we going back to the moon? There are 4 reasons. The first reason is geopolitical. Geopolitical competition. We want to, if you were over at the aerospace update, the space update earlier today in the Simone Gallery, you heard them talk, the gentleman talk about competition with China. And that's a true thing right now. We want to establish a sustained American presence on the moon before China does. And again, as I said, not just flags and footprints. Right now, China has a roadmap to build a lunar base in the South Polar region by 2035. And they plan to land taikonauts, Chinese astronauts, on the moon by 2030. And we want to be sure that we have a sustained presence before they do. Why? Well, it's because of things like this. Every human on the planet, all of you, look up every night and you see the moon. And will you all see just Chinese astronauts on it in 2035? Or will you see both Chinese and American astronauts on it? And that's kind of a big deal when we think about our presence in the world. What is the impact of every human on the planet, no matter where they live, looking up and seeing just a Chinese lunar base? They won't actually be able to see it, but they'll know they're there. And we also see, in particular, the new NASA administrator is very interested in making sure that we inspire the next generations, our current generations and the next generations of US citizens. And so having our nation inspire the world is a very important aspect of the geopolitical competition that is actually happening today. Reason number 2 is the normal one that we talk about a lot. It's exploration and science, it's understanding lunar geology, understanding lunar impact history. One of the things that the moon has is a very good record of meteorite impacts on the surface of the moon because it doesn't have an atmosphere. So the craters last a long time, and you can study the impact history and learn about our own planet. Our own planet, probably, we live in the same solar system environment, so probably exposed to the same populations of meteors and asteroids and things that would impact it. So we don't see it on the Earth because our atmosphere destroys the evidence, thank goodness. But on the moon, we still see it. So studying the moon can give us real insight into the history of the Earth. Also, a very important aspect of this new sustained presence on the moon is about resources. Where are the resources? You know, it's like the USGS, the United States Geological Survey, surveyed the western part of this country in order to find where resources are, where copper is, and where iron is, and where rare earth metals are. Rare earth metals are a big subject that we all hear about a lot today. Where are they on the moon, and might they be accessible in a different way? We'll talk more about each of these topics later. Reason number 3, we want to practice for Mars. We are going to go to Mars. Probably sometime between 2030 and 2040, the first humans will land on Mars, and we need to practice various aspects of that journey. We've got to develop and test the systems required for the journeys to Mars, and the moon is a perfect testing ground. You can't do it on the International Space Station because the environments do not accurately represent the environments that astronauts will be subjected to on the journey to Mars. And living on Mars will require lots of new technologies. How about let's test them out on the moon? Seems like a pretty good idea to me. Then the 4th reason to do this is the potential for economic growth, for resource exploitation, commercial resource exploitation. And there are various categories of that. You can use the resources on the moon. There are lots of different ways of using that. We'll talk more about water, but water, I've mentioned rare earth metals, helium-3, maybe not for use on the moon, but for use on Earth, helium-3 is a very real. In fact, there's a local Puget Sound company, Interloon. Is anybody from Interloon here? No? Okay. Interloon is working to develop helium-3 mining on the moon. Okay? And that's for use in quantum computers and for fusion. quantum computer is probably the nearer term market. But if and developing those resources is a real opportunity for use on Earth. And then for use in space, all of the above. There are lots of different economic architectures, economic systems, economic approaches that could leverage resources from the moon. And so we want to develop that potential capability. So now, once we have, so that's the why are we going back to the moon? Now we need to understand a little bit more about the requirements. And so to understand what it's going to take to go back to the moon, we need to understand where on the moon we want to go. So the Apollo missions all landed on the near side of the moon in the equatorial region. And all of those red numbers, I didn't realize the laser pointer worked. Each of these numbers is one of the Apollo landing sites. Why on the near side in the equatorial region? Because it's the safest place to land. It's got continuous communications with Earth. It's well illuminated during the day. And you get a 2-week day. Unfortunately, you also get a 2-week night. And so the astronauts had to go, they went in the lunar morning, and they stayed for up to a couple days, and then they came home before the sun set on the moon. As I mentioned, it's the best place for helium-3 in that region, and that's in fact why Interloon is focused on looking for helium-3 in the equatorial region. However, there's no water in that area. So right now, we're talking about the first sustained lunar base is going to be in the South Polar region. And the whole reason for that is because there's evidence for water ice. So we know that water ice, if we find it, could dramatically reduce the cost of sustained lunar presence, right? And we would use it to provide water for the crew, to maybe make oxygen by electrolyzing the water. We could use it to grow food on the moon. We could also use it to make liquid oxygen and liquid hydrogen to serve as propellants for lunar ascent vehicles to go from the moon back to Earth. So there are lots of reasons why we do that. And the signals from the south pole of the moon, all of those blue, the blue speckles, are where we have detected water, and the water was detected was an interesting international collaboration mission where NASA put a spectrometer on an Indian satellite. So it's a NASA data, but collected on an Indian satellite. So we get the highest signals, that's the South Pole. The crater right there in the middle is called Shackleton Crater. And that's where there is some evidence of water. However, we don't know exactly where it is. Shackleton Crater is 13 miles across. So think of something 13 miles away, and yeah, sure, someplace in there's a little bit of water signal, but we don't know exactly where it is. We don't know how the water ice is bound to minerals. We don't know how hard it is. We don't know how to drill for it, how to extract for it, and we don't know how to process it. And so one of the big challenges now is that if we want to maintain our prerogatives and ensure that the United States maintains access to water that we can use, we need to go soon, because we don't, if China, for example, or some other nation establishes a safety zone around the only accessible water, we won't be able to access it. So there's some urgency associated with this because of the uncertainty in the water. So to summarize our goals, we want a sustained American presence in the lunar South Polar region with a crew of 2 to 4 to start in the 2030s. We want it to be capable of supporting exploration and science around the surface of the moon. We want it to be capable of operating in the permanently shadowed region, which is where the water signals are strongest. We need it to be capable to grow. We want to be able to expand the surface operations to exploit local water and other resources. And hopefully, over time, over 20 years or something, we will create a new source of national economic growth. Right now, for those of you who follow the space economy, right now there is a growing, vibrant space economy, but it's all focused on low Earth orbit. There are a few satellites in geosynchronous orbit, but there's a lot of economic activity of the space economy is focused on data, taking pictures or communications or getting data from low Earth orbit. There is no space economy involving the moon today. And so the question that we need to ask ourselves is, if we see that as important, how do we start to establish the capabilities necessary to grow the economy in that way? We also want it to be extendable to Mars missions, right? To the maximum extent possible. There are going to be a lot of technologies that are unique to the moon, but to the extent possible, we want it to be extendable to Mars. And so what will it take? How do we do this? So what are the infrastructure requirements? So for people, we need habitats with highly reliable environmental control systems, right? We got to keep the people alive. They've got to have consumables. They've got to have air, food, water, either delivered from the Earth or made on the moon. For exploration and science, we've got to have instruments to do the studies, and we have to have vehicles that are capable of moving around the surface of the moon with either scientists on board or just instruments, so either robotic or crewed rovers. For commercial exploitation, we need access to water ice and the techniques to mine it and purify it. We need vehicles to mine and store the regolith, which is what we call lunar dirt, right? The surface of the moon is lunar regolith. Then we need some processing plants. And the first stage of that processing is called benefaction for anybody in the mining community. If you are interested in mining, the first stage of you extract ore from the ground and then you send it to a benefaction plant. And essentially what that does is it crushes it up into a fine powder so that the chemistry, so that you can process it and extract the useful resources. And then we need transportation, handling, and storage capability for whatever the product is. If it's liquid oxygen and liquid hydrogen for propellants, those are very, very cold. Those are cryogenic fluids, and so it takes power to store them, okay? So as you can imagine, the power requirements for commercial exploitation are the highest of all of these, but all of them take power. One of the fallacies that I hear a lot is, oh, we're going to do a lot of this with automation. We're going to have robots do it all. Excuse me, but robots take power too, right? They only, the best robots now are probably 500 watts or so. They have battery storage for maybe a few hours, and then they need to recharge. And so robots take power too. So don't, whenever you see a fancy picture of robots on the moon or Mars, ask yourself, what's powering them? Batteries will run down. So how much power will we need? So if you do the math, and many of you can do the math, but you will see that 2 to 4 people will take about 20 to 40 kilowatts of power. Right? So you can imagine your refrigerator is about a kilowatt or so. If it's really efficient, it'll be less than that, but it's something of that magnitude. And so keeping people alive, 2 to 4 people takes 20 to 40 kilowatts. 8 to 10 people will take about 100 kilowatts. Okay, so that's about what it will take. Exploration and science, I'm using the International Space Station as a model. We do a lot of science on the International Space Station, and it supports 8 to 10 people, and we can do and it has 100 kilowatts of power. So just like the International Space Station, it takes about 100 kilowatts to do exploration and science and keep 8 to 10 people alive on the surface of the moon. Robotic rovers, the rovers are going to be intermittent. It's just when you're driving that you need the power. And a robotic rover will take about 0.5 kilowatt, just like a robot will. A crewed rover, because it also will need the life support systems and all of that, will take about 5 kilowatts per rover. You can see where I'm going with this. I'm sort of trying to, get to the point where we can add up all the power and ask how much do we really need, right? For commercial resource exploitation, we got to add a fair amount more power. If it's just for water for the crew and making oxygen and air for the crew, it's going to be another 20 to 40 kilowatts depending on the crew size. So it's like double this. If you want to grow food, have a little greenhouse with lights and equipment to run and heat, moon gets cold, it's going to be another 1 to 5 kilowatts. Robotic propellant production is going to be 100 to 300 kilowatts, depending on how much, what your launch rate is. And robotic helium-3 production, so these vehicles that you see pictures of in the news, if you look up Interloon, those vehicles are going to take another 100 to 200 kilowatts or thereabouts. Might be intermittent depending on how, but for those of you who are in the business community, how would you like your capital assets to be sitting dormant 50% of the time? You wouldn't like that at all. You want to be running continuously. So you want to be operating on the surface of the moon 100% of the time in order to get the efficiency, the return on capital that you need. Metal mining and production, anything from a couple hundred kilowatts up to megawatts of power. Okay. So at the low end, we're talking about 20 to 40 kilowatts with a crew of 2 to 4 and very limited resource development, maybe a little bit of what's called in situ resource utilization. At the high end, we're talking about 100 kilowatts to megawatts of power over time. Again, you don't need all of this at first, but you need enough at first to have a sustained presence. So, what are our options for power on the moon? Well, there's no atmosphere on the moon, there are no clouds, and there are a few mountain peaks near the South Pole that get sunlight up to about 70% of the time because, they're at the polar region, and so they're high altitude, so they get exposed to a fair amount of light. So solar power should be great, solar power with batteries, right? Well, except for the fact that for most of the moon, the night is 2 weeks long. So you need a really big battery system. Is there anybody here that has a solar battery system at home? Sort of, some people. So you know how big your batteries are to just run through the 12-hour night. What if your night was 2 weeks, 24 hours times 14 days? That's a really big battery system, and I'll show you some numbers in a minute. Or we could possibly beam power from a sunlit solar array to where we need it. So there are two options there. So the analysis that had to be done and has been done is you got to compare the systems for power level, time and darkness, power level and darkness, and the need for mobility. And we are, as I warned some of you at the beginning of this, we are going to geek out a little bit. So there's a little bit of data. So the blue circles, so this is a plot of power in kilowatts. It's a log plot, so it goes 0.1, 1, 10, 100, 1,000, and 10,000, versus time and darkness. So this is the time and darkness. And this is what it is in low Earth orbit for like the International Space Station, where it goes around the Earth, so it spends about half of its orbit in dark, and the rest is the solar arrays are illuminated. So even the International Space Station has a big battery system, actually, that my former team built. They built it in Los Angeles, and it works really well. Anyway, so if you look at the mass, so this is the weight, the size of the circle is the mass of the power system. So bigger circle means it's heavier. So green is solar, a solar system, a solar power system for a lunar night, in this case, would weigh around at 10 kilowatts. So 10 kilowatts, come over here to lunar night, 2 weeks long. A solar power with battery would weigh 150 tons. 150 tons. A nuclear power system weighs about 15 tons. Actually, no, for 10 kilowatts, it weighs about 3 tons, 3 or 4 tons. So what this starts to tell you is that if you scale up in power, so if we start to need 100 kilowatts, the International Space Station is here, right? The International Space Station is about here. That's in low Earth orbit. But if we go to a lunar night, it turns out to be 1,000 tons of batteries that you would need to survive the lunar night, to operate through the lunar night at 100 kilowatts. So this is the kind of data that you need in order to compare the different options. Now, there's another little piece of data down here, the power beaming. This is for 3 different types of power systems. There's solar and power beaming, solar and batteries, and fission power, so nuclear here. So power beaming is good if you only need up to, around a kilowatt at most. Then you could actually beam power, and it seems the architecture seems to work pretty well. Solar and batteries looks applicable to in the tens of kilowatts, maybe 20 kilowatts, but only for time and darkness up to around 10 hours. So they're only, and 70% is, if you do the math, 70% of 29 days, it's several hundred hours. So you're still out here, even with 70% illumination. So this is why space nuclear systems for the moon are the best choice if we want to operate at scale on the surface of the moon. So for power levels greater than about 10 kilowatts and dark periods greater than about 20 hours, nuclear power systems are lighter. They're a lot lighter than solar and batteries. And power beaming doesn't scale very well. You will want power beaming for those robotic rovers. And so just like on Earth, on the moon, we're going to have a power system that has all of the above, right? We need all of the above. We need solar and battery for some places and some applications. We're going to want solar and power beaming for others. But if we want to scale our operations on the surface of the moon to greater than 10 kilowatts in places where it's dark for more than 20 hours, we need nuclear power. The other really cool thing is there's a lot of work in the last 10 years on terrestrial microreactors and mobile reactor systems, both on the commercial side and defense, national defense. And that work has created many opportunities for the space reactor community to take advantage of that work. And I'll talk more about that in a little bit, about the advances in terrestrial reactors. So now we're going to, again, continue to geek out a little bit. I just want to make sure we're all on the same page as we start to move into talking about this nuclear reactor subsystems and their status, that we're all on the same page about what is a thermal power system. And that's what we're talking about. All of our power plants, be they coal-fired or natural gas-fired or any of those, are all thermal power plants. And they use a heat source of some sort, some heat source, and you transfer the heat to what we call a power conversion system, and some fraction of that power of that heat is converted by the power conversion system into electricity. And that's usually between 25 and 35%. All the rest of the heat is rejected as waste. You have to get rid of it. And on Earth, the big stacks that we see on power plants, that's how they get rid of the heat, excess heat, with air cooling or water cooling, or they cool somehow, and that's how you get rid of the waste heat. And then that electrical power goes to what we call a power management and distribution system, which is just a fancy way of saying that That's how we make sure the voltage is right and it provides the current to the different loads. So you will see in some future charts, I will talk about the efficiency of the power conversion system, and that's really what this is. It's the fraction of the power created by the heat source that is converted to electricity. So what we're talking about here is using a nuclear reactor as your heat source. We'll talk more about the power conversion system. We'll talk about the heat rejection, which again, as I mentioned, is completely different in space than it is on Earth. On Earth, we have air and water. It requires a radiator in space. And we'll talk about what are the parameters that go into the size of radiators in space. And then we'll also talk a little tiny bit about the PMAD. The PMAD, the Power Management and Distribution System, I think the complexity is that a lot of us, we plug things into the wall and we think, oh, that's really easy. Well, you can just do that. Well, no, you really can't. The power system has to adjust every time you plug something into the wall, right? And there's a small adjustment that needs to happen. And if you have a system failure in your load, then the power system has to adjust quickly. So you got to account for all of that in your design. So for nuclear, I'm going to walk through the major elements of this. And again, I promised a little geek out, so it's going to get a little technical, just a little bit. Hopefully not too much. So for nuclear reactors, there are two primary options. One is called a gas-cooled reactor, and that is where you have a reactor and shield to protect protect the electronics in the power conversion system from radiation. And then you have a power conversion system. So just like I showed you in the prior chart, you've got a radiator, that's your heat rejection system, right? And then the PMAD. So this is essentially the same chart I just showed you, but it's got a little bit more detail because it's got a reactor and a shield. And for a gas-cooled reactor, you just use gas, cold gas. You send cold gas through the reactor and it gets hot here, and then you take that hot fluid back here and it goes into the power conversion system. And the power conversion system might be a turbine, and I'll talk more about that, but there are several different kinds of power conversion. And then the waste heat, you got to have radiator coolant loops. So you got to get the heat away from the waste heat, away from the power conversion system, and the good electricity comes out through the PMAD. That's one of them. Then you have the heat pipe reactor. And heat pipes are essentially sealed tubes that use a phase change to carry heat from a hot end to a cold end to transport heat. And so here you have the same reactor shield, but you have the addition of a heat exchanger. And the heat exchanger is where you heat up the fluid that drives your power conversion system. So again, it's the same general idea, but this is a heat pipe reactor and a gas-cooled reactor. So you're all going to there will be a quiz on your way out, and you're all going to have to prove to me that, okay. So those are the two different types of reactor approaches that are being considered now. There are challenges for each of them. On the gas-cooled reactor, the reactor pressure vessel can be quite heavy because it has to take the pressure of that gas. And it also, if it's hit by a meteorite, if that pressure vessel is hit by a meteorite, that could get exciting. And we don't like excitement. We want boring, right? And then on the heat pipe reactor, the challenge is there's this extra heat exchanger, and that is an efficiency loss, right? So some of that heat gets lost in the heat exchanger. So those are the challenges for the two different types of reactor. Don't freak out. It's just a little bit more geeking. So what are they looking at today in reactor technology? Well, they're looking at different fuels, moderator, structure, cooling, and configuration options. So this is a picture of, this is a cross-section of a reactor where you have the fuel pins, and we'll talk more about the fuel in just a second, but you have got fuel pins, and then there are what are called neutron reflectors, and control drums for the reactor. And on the left here, you have a heat pipe reactor. So these are heat pipes that are taking the heat from the reactor to the power conversion system. And on the right, you can see the cold air coming, or the cold gas coming in here down at the bottom, and it cools the reactor. It takes the heat from the reactor back to the power conversion system. So you're all going to be power plant experts at the end of this talk, right? And then obviously in the reactor, there's a pressure vessel, there's a vessel on the outside, and you may have cooling depending on the kind of. So a lot of this work is actually leveraging work on terrestrial reactors. So it's the same kind of work. So critical advances in terrestrial reactors. So one of the things that happened in the last 15, 20 years at most is the development of what we call high-assay, low-enriched uranium. I forgot to talk about that on the prior chart, but you can see here the fuel of the reactor is either what's called highly enriched uranium, where they take uranium ore and they purify to a specific isotope of uranium, U-235. And for highly enriched uranium, you get that purity up to 95% or better. For high-assay, low-enriched uranium, it's less than 20% U-235. The big reactors that we have that drive our power plants, those are like 5% U-235. They're very much lower uranium purity levels, U-235 levels than we're talking about here. One of the things that this enabled, the development of HALEU reactors, was shrinking of the reactor sizes. The total mass of the reactor got less because the purity of U-235 went up. But we stay away from 95%, the highly enriched. Highly enriched uranium is used in nuclear weapons, and we don't want to go close to that if we can avoid it, okay? So 20% is about as high as you can, in fact, by law in the United States, 20% is as high as you can go commercially. It's got to be a US government organization that if you get up to highly enriched uranium, it cannot be commercial. It's got to be US government owned. So that's a big distinction, and one of the major advances that happened was the development of HALEU reactors. Because it's much less regulated than HEU, for a very good reason, and it's enabled lots of companies to compete in the development of advanced reactors. And you know, our nation, we are a capitalist nation, and we like competition. We want to have multiple competitors developing technologies. And the development of HALEU fueled reactors enabled that for nuclear power systems. So it was a big deal. In addition, commercial companies always are trying to reduce their costs, and they do that by increasing automation. And so there's been a lot of development in automating nuclear reactor operations, and that's really important for space, right? Because a lot of times space is going to be unattended. You want to be able to operate it like a nuclear robot, right? You don't want to have a person there controlling dials. And so that development of better sensors and control systems for reactors on the terrestrial side has really helped the development of space reactors. Right now, what are called small modular reactors and micro modular reactors, the SMRs and MMRs, they're used for mobile power sources on the military side for forward bases and disaster release, or they will be as they get developed. And also, of course, carbon-free power for distributed data centers and ships. I think Norway just completed an assessment of using small micro-modular reactors on ships in order to get carbon-free, eliminate the carbon coming out of the stacks. So the development of multiple venture capital funded terrestrial SMRs and MMRs has established a commercial marketplace for advanced reactors. And that's new. That did not happen. That has only happened in the last 10 to 15 years. So that's on the reactor side. On the power conversion side, again, we're still geeking out a little bit. There are really 5 different ways of converting heat to electrical power. There's thermoelectric. Thermoelectric is like, for those of you who know thermocouples, if you know, electrical temperature sensors. If you hook up a whole bunch of those, like thousands of them, in a series parallel network, you can get voltages and currents and powers of interest. But their efficiency is super low. So this is a table of the concepts and different characteristics of them. And see the efficiency here? That's the efficiency of power conversion, like I showed you before. So the demonstrated power for thermoelectrics, less than a kilowatt, and they do not scale well. There's something called thermionic and thermophotovoltaic power conversion. Thermionic is you get a surface of a metal really, really, really hot, and electrons start coming off it and create a current, and you can get power that way. Right now, they're very inefficient, but there are programs underway to make them actually very relevant and competitive for space nuclear power system, and that's at the University of Michigan. If there are any students here, there are several university programs that you should look into if you're thinking about doing research in space nuclear systems. Thermophotovoltaic is where you get a surface hot and it starts to glow. And then you use a solar cell optimized for infrared to convert that radiant energy, the heat, the light that's being emitted from the hot surface into electricity. So it's essentially you're just creating an artificial light source that you then use a solar cell. And those are actually very high efficiency. The problem with them is they don't work well in the sun. They don't work well when they get hot. And so if you get a TPV, nobody likes to say thermophotovoltaic, so they say TPV instead. So if you get a TPV system too hot, they're semiconductors and they stop working. They get very inefficient. And they're also susceptible to radiation damage, which kind of sucks when you want to be close to a nuclear reactor. So there's a lot of work going on now to try to mitigate those issues. But so TPV, if we could get 40%, that'd be great. But the two leading candidates today are the last two. Closed Brayton cycles, gas turbine, so it's just a gas turbine essentially, but you have to close the cycle, and I'll talk more about that in a minute, and Stirling reciprocating pistons. And these are just, again, two ways of creating electricity using heat. And there's been a fair amount of work done on both of these. Still a lot of work still to do, but these are the most advanced systems today. And this, probably the three top options for nuclear power systems on the moon are the closed Brayton cycle, the Stirling, and the thermionic. Thermionic is probably a second generation. It's still research. Okay, some history. We've actually flown a space nuclear reactor. In 1965, we launched SNAP-10A. And it used high enriched uranium fuel, so you're now all experts. So when I say it used HEU fuel, you know exactly what that means, right? It was a 30 kilowatt thermal power. It used pump liquid metal heat transfer to the power conversion system. So all of these terms should start making some sense. It used a thermoelectric conversion system. So again, that first one. That today, thermoelectrics are used on plutonium power sources, like on the rovers on Mars. If you know the rovers on Mars, they're all powered using thermoelectrics. And there are good reasons for that. There are also good reasons to say they don't scale very well to very high powers. So, but back in 1965, we launched a thermoelectric power conversion system. It was only 2% efficient. It really kind of sucked, but it worked. It was launched into 1,300 kilometers, operated for 43 days, and then a voltage converter separate from the nuclear power system failed, and it's derelict. But it's still up there in orbit, 1,300 kilometers up. So there's an American nuclear reactor in orbit today. So I was going to talk a little bit more about the power conversion systems that are probably going to be used today. There's the Stirling reciprocating piston and the Brayton gas turbine. So the Stirling is a piston that moves back and forth in this, and there's a linear motor that converts that motion to electricity, and then there's a gas turbine. I'll talk a little bit more about that. But this is a schematic of a system that was designed to provide several kilowatts of power on the surface of the moon. If your power level, there's some challenges, some technical challenges that I'm happy to talk about when we have time, with Stirling, with scaling, making Stirling work above about 40 kilowatts. It can, but it's challenging. And so if we want to do that commercial economy or really grow lunar resources, Stirling probably isn't the answer there. Closed Brayton cycle is a very promising answer to near-term solutions for powers greater than 40 kilowatts. And it easily could provide up to a couple hundred megawatts if we had such a big reactor and heat rejection system. Again, you need to get the reactor hot. And so that means that your power conversion system has to operate with temperatures of over 1,000 degrees Kelvin. There were two other big nuclear programs. They did not fly. They just did some development testing. The SP-100 program in the 80s and 90s, that was targeted 100 kilowatts for orbital power. It also used HEU fuel. Okay, so that 95% or higher uranium-235, used a pump liquid metal, thermoelectric power conversion again. And the program was canceled really because we found other ways of getting the 100 kilo, or the power that we needed. There were improvements in other aspects of the mission. So that program was canceled. And then much more recently, some of you may recall Project Prometheus, which was to do outer planet. It was called also the Jupiter Icy Moons Orbiter. And so it was a big spacecraft, 200 kilowatts for space propulsion, also used HEU fuel, so highly enriched uranium. And they had not decided yet exactly which reactor option, either gas-cooled or heat pipe reactor. And the program was canceled in 2005 because their budget, their costs, their initial budgets were pretty low. And so it was limited to subscale work. Okay. So the Brayton, I just want to, don't worry, I'm not going to go into much detail here, but the closed Brayton cycle system, the key is this is a gas turbine, just a standard gas turbine, right? And there are pictures over here of some hardware from an extended test. The standard gas turbine here's the reactor, and the hot gas comes out of the reactor, spins the turbine around, which drives the generator and takes power to the PMAD, right? Just like I showed you before. The turbine also drives a compressor, and the gas has to come out of the turbine, go to what's called a recuperator, another heat exchanger, and the waste heat goes to the radiator. Remember, that's how you get rid of waste heat in the radiator. And then there's what's called an accumulator and a filter, et cetera, and then it goes into a compressor and the cycle repeats. The key here is this is closed. It's a closed system. Nothing escapes this closed power conversion system. So again, the turbine is just like any other gas turbine, right? GE Vernova today sells gas turbines with turbine inlet temperatures of 1,500 degrees, much hotter than what we need for space nuclear. It'd be nice, but this is hotter. The generator is a standard alternator. So it's just like you have in your car. It's an electric motor run in reverse. The key difference is it's a closed cycle, and you need that recuperator in order to close that cycle. And there's an efficiency hit from that, but it allows you to operate without wasting any gas, because in space, there's no way to replenish that. So you have to close the cycle. Some recent testing using a Stirling power conversion system. So again, this is a reciprocating pump, reciprocating piston power conversion system. This was actually tested at the Nevada test site in 2018. It used, again, HEU fuel. It had a peak temperature of about 1,100 Kelvin. It used sodium heat pipe, so it was a heat pipe reactor, not a gas-cooled reactor. It used 2 Stirling power conversions. It didn't test the radiator, the heat rejection system at all. They just used a water loop to cool things down. Demonstrated all operational phases of the reactor, which was pretty cool. It's pretty major progress. But it was a really tiny reactor. It was only 4 kilowatts thermal, only created 160 watts of electricity. So remember, we need 20 to 40 kilowatts. So a lot more than this. This is many factors lower. But it did demonstrate a lot of this. And this is a picture of what a 1,000 watt, a 1 kilowatt system would look like. These are the reactors down here, the Stirling power converters here, and then their heat pipes taking the waste heat to the radiator. Want to talk a little bit about radiators, and it's important to realize how radiators scale. Radiators get bigger if you need more power, right? But if you get them hot, a really cool thing happens, not literally. If you get them hot, they get smaller as temperature to the 4th power. And for those students in the room, that's called the Stefan Boltzmann law, and you can go look it up. There's a great Wikipedia article about it, but that is the law that determines the size of the radiators. And on the International Space Station, these are the big solar arrays that create about 200 kilowatts of power, and then they charge the batteries. And remember, it's half of the orbit is at night. So then they're generating 0 power. So to generate an average of 100 kilowatts, they need 200 kilowatts of arrays in order to do that. So these solar arrays are sized for about 200 kilowatts. And then these are all the radiators to keep it cool. And they're ammonia pumped. They pump ammonia through them in order to get the heat out of the space station out to the radiators. So, and you can see how big they are compared to the ISS. As the efficiency of the power conversion system goes down, then there's more waste heat. And so the radiator size has to get bigger. But if you can get it hotter, then it gets smaller very quickly because it goes as T to the 4th, temperature to the 4th power. Sorry, the geeking out is almost over. Okay. So, as I mentioned, on the space station, they use ammonia, and they just pump ammonia through a loop. In this case, ammonia wouldn't work because the temperatures are too high. So this is the heat exchange. This is the waste power. The waste heat from the power conversion system comes into a heat exchanger, and then it goes, the hot liquid comes out here, and these are the radiator panels, and you would size that depending on the power level that you have. And then after all of that, after it radiates the heat away, of course, the temperature's coming down, and then you have a much cooler liquid. It's still fairly hot. It still would boil water, but it's a lot colder. So there are various trade-offs in designing these systems that you have to have this operate in space, in the vacuum of space. So what does that look like for a 10 kilowatt system on the surface of the moon? You could get away, for example, with this big plate radiator. So here, this is a Stirling power conversion system on the surface of the moon. The reactors down here, these are the Stirling converters, and then you use heat pipes, and the heat pipes come out here, and you have this big flat plate radiator facing up. A 40 kilowatt system, you can't do that anymore, so you need this really tall sail that you'd make to get rid of the waste heat. And the radiator configuration, as I said, it depends on the power level, the heat rejection temperature, and how you're going to deploy it. Okay? So, what are some system constraints? We're getting to the end, folks. What are some system constraints for space nuclear power systems, including the moon? Obviously, it's got to be safe. It's got to be launched, landed, and deployed. And so it's got to be safe, it's got to have the right mass, it can't be too heavy to launch, and it's got to fit within the shroud. You're going to have to build it on Earth, you're going to have to test it. So there are going to be terrestrial operations. You got to be able to take it to the launch site, load it on the rocket, launch it, take it to the moon, land it. It's got to operate and then be disposed of. All of that's got to be safe. Deployment is going to involve offloading it. So if you've got like Starship, we all see the pictures of Starship on the surface of the moon. The door is way up at the top. It's got to be light enough to get on the elevator and come down. And then when it's on the ground, it's got to be loaded onto some kind of a motion get away from the lander. Okay? So there's a lot of operations on the surface of the moon that will have to happen. You might integrate the reactor with the lander, but right now we're really talking about this approach, about deployment. Electronics don't like radiation, usually, and so you've got to protect the electronics both from the reactor and also from the radiation on the surface of the moon. You've got to worry a little bit about what happens with the regolith after you operate the reactor. Does it get irradiated? We don't really know yet. And then there are temperature variations. The lunar night is super cold. The lunar day is actually very hot. And so that radiator has to work throughout that entire range of temperatures. There have been several programs recently that have established potential designs for 40 to 50 kilowatt reactors on the surface of the moon. And this is just one example from NASA. You can all look it up. The paper down is at the bottom. There were a lot of references that I included in the talk. So I usually have the paper. And Steve Olson is a good friend, and he leads a team at NASA Glenn studying these things. And so this is a picture of a 40 kilowatt Stirling-based power conversion system deployed on the surface of the moon. And again, you have to worry about the solar radiation flux, the solar heat hitting the radiator. You've got to be, as I mentioned, you have to be able to deploy it. There are reflections from the lunar surface. So there are various complexities that go into the design of a power system that has to operate on the surface of the moon through the day and night cycles. The angle of this relative to the sun is very important. And of course, that has to work through the different seasons. The angle of the moon is tilted. And so as over an 18-year period, it actually moves back and forth. So over the 10-year life of a reactor, it's going to move. So you got to think ahead about the angle of the radiator with respect to the sun. And don't worry, I'm not going to go through this, but I do refer you to the paper that goes into a lot of detail. Steve and his team did a great job of looking at putting the 40 kilowatt fission surface power system into a lander envelope, so making sure it fit on a lander and it could be actually physically landed. Then putting it on a rover and moving it to where you want to deploy it. And then the deployment sequence. And they have mass estimates for everything. And it actually ended up weighing about 10 tons, so 10,000 kilograms for a 40 kilowatt reactor system on the surface of the moon. The final topic is extensibility to Mars. And the nice thing about Mars is it has an atmosphere. The thing that makes Mars a challenge is it doesn't have much of an atmosphere. It's thin. And so one of the things about Mars, that thin atmosphere means that dust storms persist. And we've all heard of Martian dust storms. Turns out it's not about the dust landing on the surface that you're trying to keep cool. It's about the solar flux. That's why we need nuclear power on Mars, is because the atmosphere gets really dirty and opaque during a dust storm. And so solar panels don't work anymore. So it's interesting because on the moon, the reason you need nuclear is the night. On Mars, the reason you need nuclear is dust storms. So those are the two different reasons. It's kind of interesting. But as I mentioned, you do have a little bit of an atmosphere, and that means you can make fan-based convective cooling systems. So now we don't need the big radiator. We can just have these fancy fan systems to cool to deal with the waste heat from your power conversion system. But you would use exactly the same reactor, power conversion system, and PMAD, and power management and distribution, exactly the same as you use on the moon, but the heat rejection system is completely different. Okay? So designing a system for the moon gets you 3/4 of the way to Mars. And then for nuclear electric propulsion, you can do the same thing. You use the same reactor, power conversion system, and radiator technology. You configure it very differently. Here's a spacecraft that was designed. This was done by Aerojet Rocketdyne, my former colleagues. The reactor is out here. There's a shield. Power conversion system is out here on the far right. Then you have the radiators, and you have the electric propulsion system here at the back. And this is a 50 kilowatt nuclear electric propulsion vehicle designed to orbit Neptune, okay? It takes a big, anyway, the paper is available if you just Google Aerojet Rocketdyne NEP Neptune orbiter, it'll come up. It used two different kinds of, or looked at trading different kinds of ion thrusters, but again, from a power system perspective, it used the same exact reactor shield power conversion system, and in fact, they use the same PMAD. It might be better to change the PMAD a little bit, but anyway. So the point is that developing nuclear power systems for the moon is a stepping stone to Mars and beyond. And that's a very important aspect of this whole effort. So right now, NASA has actually issued 2 draft RFPs today. I mean, not today, in the last few months, for fission surface power. And the final RFP is expected within about a month. And they're going to require some form of public-private partnership. So they don't want to make it just NASA, just the tax dollars, just you all paying for it. They also want companies to invest. And so that's a big change. And so the goal is to have a significant space nuclear demonstration by 2028 and a reactor on the moon by 2030. And again, the geopolitical pressures are what's driving a lot of this. And NASA's partnering with the Department of Energy. There was just an announcement a couple days ago about that partnership. They've signed an agreement to leverage the DOE's. So this is like Idaho National Labs right next door. Idaho National Labs is very heavily involved in this program, in this effort. And Idaho National Labs also has a lot of test capabilities, and so do other national labs, but Idaho in particular is doing a lot of work on fission surface power systems. And lots of companies, there are several companies out there that are working on various approaches to this technology. So, bottom line, what future do you want in space? That's really the question that you have to ask. Because if you want a future where the United States leads in the development of a sustained lunar presence and the development of a potential space nuclear, lunar economy, we need space nuclear power. We can do this by 2030 with a focused effort. I spent a lot of last year looking at this challenge, and there are many challenges, but it's doable if we put the investment in and we do a real focused effort. And they do provide a foundation for Mars and beyond. And I hope that I've convinced you of that. And that's it. Thanks for putting up with me.
Do Q&A. If you have a question for Roger, please do come down to one of these microphones in the front of the room and ask your question into it. I'll kick things off, Roger. Just a quick question about those RFPs. Is there a minimum spec requirement on those? As in, is it more important to just get something there sooner and maybe replace it?
So NASA has focused. They at first they just finished 2-year programs to design initial 40 kilowatt systems about a year ago. And then the interim NASA administrator, Sean Duffy, Secretary Duffy, announced actually after we published our report that he wanted 100 kilowatts on the surface of the moon. And now it's not clear. The feedback from industry is there isn't a market for power on the surface of the moon. And so the question is 100 kilowatts too much? And so the final RFP will tell exactly what they're doing, but it's probably going to be something in the 40 to 100 kilowatt power range in terms of minimum power level. But 2028 is when they want a real demo, and 2030 is when they want an operational surface system on the surface of the moon.
Thank you for a great talk. My question is about the relative energy density of highly enriched uranium relative to, I forget the term.
HALEU,
HALEU.
high assay, low enriched uranium. It's not a risk of explosion. It's actually, by US law, the only organizations that can own HEU, highly enriched uranium, are government organizations. So if you want to spawn a commercial, if you,
So it's more of a commercial limitation in terms of development than
yeah,
sort of.
it is. And so it enabled the creation of this new marketplace, this competitive environment for the development of advanced reactors, which we never had before, right? There was competition for big power reactors, but those are at 5% enrichment. The small reactors and the micromodular reactors, to make them that small, you need to increase the enrichment. And in order to do that, we needed to go above the 5% to HALEU, but we needed to stay below the threshold that requires US government ownership. There's one company on the planet or one company in the United States that can handle highly enriched uranium, and that's BWXT in West Virginia. And they do a great job. They do the reactors for the nuclear navy, right? Great company, but there's no competition. They're very expensive. We need competition, so that's where HALEU comes in. Yes, sir.
Thank you. Very fascinating and mind-boggling presentation, dare I say, for us non-scientists. Kind of a two-part question. So the power management and distribution, maybe this is still being sorted out, but once the power is generated, how is it distributed, like to the various electrical need? Would it be underground cables or?
Probably not underground. You'd probably just lay the cables on the surface of the moon, at least at first.
It'd be like surface cables.
Absolutely. For the high powers, so one of the things that you might do, for example, when you're thinking about the overall infrastructure, power infrastructure on the surface of the moon, in order to enable a large number of customers, you would have high power users with wires, which are very efficient to transmit power. And so you'd have to string wires, just lay them on the surface to the loads, like to the habitat, which takes 20 to 40 kilowatts all by itself. But for the intermittent uses on the rovers, you might use a beam power system, which is like a laser, and on the rover you have an optimized solar, like a solar cell that's optimized for that for the wavelength of the laser, and so you could beam power at 0.5 kilowatt to a whole bunch of different rovers if you wanted to. So there's some really cool architectures. Again, we're talking about how to set up a power grid on the moon.
And then just the second part, real quick, sort of a bureaucratic question, if you will. On one of those last slides, you mentioned the RFP process that's underway. You said there was 2 draft RFPs and then a final RFP coming out. So was the idea the draft RFPs were sort of trying to solicit interest?
Yes, and solicit interest and feedback. So
feedback about how this would work.
feedback, exactly. So the report that Kale mentioned during the introduction, the weighing the options, the strategic leadership, you can actually, that I co-authored last year, it goes into a lot of these questions, and you can download it for free if you just Google, my name, Roger Myers, and the title that Kale mentioned, Weighing the Future of Strategic Options for Space, for U.S. Leadership in Space Nuclear Technologies. It's free. It's on a Department of Energy website, and you can explore that to your heart's content. And some of these questions are addressed in there.
The final RFP is just soliciting the final proposal.
Yeah, one of the challenges with the RFP process is that in the report we wanted more commercial investment, because all these venture capitalists are investing in terrestrial system, and we're asking, why can't we extend that to the moon, to power for the moon? And so there's been a lot of debate about that as a result of that report. And the initial RFP wanted more investment than was really sustainable from commercial industry. So there's been a lot of argument and debate about, Is it a 40 kilowatt system? Is it a 100 kilowatt system? Is it pure private? Is it 20% private? What is the cost sharing, the model for that contract? And so that's why there have been 2 drafts, because there's been a lot of industry feedback. And the final draft is due in about a month or so. We'll see when it actually comes out.
Thank you.
Yes.
One thing I was wondering on this is how long does this core last, this reactor last?
The design is the target is 10 years. So it's got to be unattended for 10 years.
Every couple of years.
And that's one of the challenges, absolutely. We don't want to have to refuel it every couple of years. And so you need to design the fuel, the size of the reactor and its burn rate to get about 10 years of operation is what the target is. Yes.
Yeah, most of our space probes and equipment, once it stops working, is left as trash. All the Apollo equipment doesn't work anymore.
Yeah.
I thought I saw a blib about deployment and
Disposal. Absolutely.
How's that?
You'd probably just bury it at first. I mean, for the first couple, you'd bury them. And again, these are very small reactors. These reactors are the size of your washing machine. These are not big things. And so the thought is that by the end of life, after 10 years, we would have enough infrastructure there to dig a hole and bury the reactor.
All right, that makes sense.
Yes. Do you have a question?
How will we get to Mars?
So that's a great question, and you should ask Cale to have me come give a different talk about Mars transportation options, because I spent a lot of time thinking about that and working on those. So how will we get to Mars? There are a couple different ways. It's going to involve a big rocket or lots of big rockets, and it's going to involve taking like a piece of the space station and a habitat and taking and letting the astronauts live in that while the rocket takes them to Mars. And because it's going to take probably between 6 and 9 months to get to Mars for the first few journeys. So it's going to take a long time. It's going to be pretty lonely out there. So that's how we're going to get there, with big rockets.
Thank you, Dr. Myers, for coming out today. It's a really interesting presentation. Probably one topic that is probably in the news cycle these days is probably also fusion power, which you haven't really gone into in the presentation. So I want to
Sure.
a little bit of time in the Q&A.
Sure, I'd be happy to talk about fusion. I've spent a lot of time looking at fusion, and actually when Bhavya and I started looking at this, we were hoping that fusion, the development track, given the amount of investment in fusion today, would be fast enough to enable that to be the first step. Unfortunately, our review of fusion technology showed that it's probably still out further than we need to meet our timelines. Our timelines are driven by the geopolitical competition issues and that challenge of 2030 to 2035, that early 2030s timeframe, and needing to establish the infrastructure. And fusion, there may be, I'd like there to be one break-even demonstration that doesn't involve a terawatt laser. And as soon as that demonstration happens, I will get much more excited about the nearer opportunities for fusion.
In your discussion, you talked a lot about a couple of things. One being the radiation on the surface, the other being the big temperature swings on the surface. But I nowhere in there saw any discussion of like geothermal, where it's embedded in the surface, where you get a more even temperature for both its environment and for its ability to not have to deal with those big swings of temperature, which would make your...
And you're right, that is not being considered much now, because for the first reactor, we're not going to have the infrastructure in place to dig the hole to bury the reactor and enable that distribution of heat and using geothermal, lunar thermal, what would it be called, on the moon. I think if we don't know, part of the problem is uncertainty. We don't know enough about the lunar surface or the temperature distribution as you go down into the surface to know how that would behave. We don't know enough about the thermal conductivity of the regolith as a function of depth, for example. So there are so many unknowns that right now people are just saying, let's do something that we know will work. This will definitely work. And then as we learn more, maybe we can do it differently. Absolutely.
The first thing, the weights for your power storage, should you consider fuel cells, being that the reactant could be mined out of the ground there, at least we're hoping.
We did consider fuel cells. The problem is the mass of the infrastructure you need to mine, to do that mining and to get the purify the water and all of that. For the initial set of missions, for the first 5 or 10 years, it didn't look like it made sense in the analysis because you have to amortize the cost of all of that infrastructure over that. Now, once that infrastructure is established and is being used to keep the crew alive or to make propellants for Earth return vehicles or whatever it's used for, then that infrastructure could also be used for fuel cells, and then it might work. But we did not look at it because we were really focused on the first few missions.
Next question is, I saw that we're talking uranium-fueled reactors, but we didn't, have we tossed out thorium salts or other?
It's really mass. The uranium reactors are lighter, and so that's why.
Okay.
We did toss them out, but there's a good reason.
A really good presentation. Thanks so much.
Happy to do it. Yes?
Could you accidentally turn the soil radioactive?
On the moon, yes, you could. Just locally, right underneath the reactor, it's possible that some amount of the ground around the reactor would become radioactive. Again, this is like the size of your washing machine. So you might have a little bit of radiation. And in fact, I mentioned that the regolith is the ground, is the soil. And so right around it, right underneath it, for a few centimeters underneath it, it might get radioactive. Yes.
Thank you.
Great questions.
But they have those power plant or power sources that he uses to.
The plutonium ones.
Yes.
Yes, the MMRTGs.
Is that feasible? Is that
So no, those are flying today. So today we are flying radioisotope thermoelectric power generators, RTGs. And they are a few kilograms of plutonium, nasty stuff, but a few kilograms of plutonium with arrays of thermoelectric power converters on it to generate about 100 watts of electricity. So both Curiosity, who knows about Curiosity and Perseverance? Okay, so these rovers are on the surface of Mars today, and Curiosity's been on since 2012, so 13 years. And I actually led the development. I was the program director for the development of the engines that landed on Mars. And also a different part of our team at Aerojet built the plutonium power systems. We didn't fuel them because plutonium is very dangerous and can be used to build nuclear weapons. And so only US government agencies can handle plutonium. So Aerojet built the power conversion system and the structure to hold it, and then we shipped it to Idaho National Labs, and in Idaho National Labs they put the plutonium in and then they shipped it to the launch site. Okay, and so that was all done and those systems operate really well, but they're very low efficiency and they generate only about 100 watts, so about 1/1000th as much as we need in this case. So they work great for things like communication, like Matt Damon did on The Martian, but they do not work if you want to stay alive. He wasn't using those little power systems to stay alive to run he had that big solar array that he was sweeping at the beginning of the movie, and the windstorm came and he was out cleaning the dust off of it. There's a little bit of fiction in there, but that's okay. It was a great movie, great book too. Okay, I think hope I answered your question. Yes, sir. Or yes, ma'am. Sorry. Of course.
How many things that we're working on, such as trying to find power and stuff on space, how are they helping on Earth? I know there's helium, the fusion power plant, but other than that, are there any other?
All of the work in space has helped us on Earth. I shouldn't say all. A lot of the work that we do, a lot of the development, a lot of the technologies, a lot of the systems that we build for space, there are ways that many aspects of those systems are used on Earth. Computers were first developed for, the Department of Defense did the very first computer, or the first operational computer, I should say. But NASA developed some of the most advanced computers for the Apollo landing, and they found their way into operational use. I mean, there's a lot of different examples of that.
Thank you for the fantastic presentation. Throughout the course of it, you mentioned several research opportunities that were ongoing. If you were a hypothetical person looking at possibly getting into some sort of graduate level research in the next 2 to 5 years, are there any particular programs or areas of research you would keep an eye on?
Yeah, I think I mentioned specifically the program at the University of Michigan. It's called the SPAR program, and it's being funded by the Space Force to develop space nuclear electric propulsion systems. So it's got a reactor and a power conversion system and the heat rejection system, and then they put an electric propulsion system like I showed you the picture of. And so they are working on next generation power conversion technologies. Power conversion is the thing that drives all of the rest of the system. You want the highest efficiency power conversion system, but it needs to reject heat at the highest possible temperature in order to keep the radiator small. So there's a trade there, and there's an optimization process. So I would say that is probably the most important near term. There are lots of different aspects of the research programs. There are various challenges in the reactor design, heat pipe design, the heat transfer mechanisms. PMAD is challenging from the perspective of the dynamic nature of loads. So there's a fair amount of R&D there, but the big hitters are power conversion and heat rejection. The other interesting thing is, and I didn't talk about this at all, for in the future, nuclear electric propulsion systems offer the fastest, other than fusion, offer the fastest transfers to Mars because they enable you to use very, very high specific impulse propulsion systems. And again, Kale can have me back to talk about next generation Mars propulsion architectures if you all want. So if you want to go to Mars in under 2 months, you use a 100 megawatt nuclear electric propulsion system. The challenge there is that there is also no high power, no electric propulsion system that can operate at those power levels. So that as you go up in power, there are other research opportunities that come to the fore. Now, those are farther in the future, right? Right now, we're talking about 50 kilowatts to 100 kilowatts. We're not talking about 100 megawatts. That's another, factor of 1,000. Reactors today on Earth produce that much power, but they're huge, right? They're also all LEU, right? So they're low enriched uranium reactors. And so, and also from a power conversion system, as I mentioned, GE Vernova, you can today, if you had enough money, you could buy a gas turbine, a Brayton gas turbine at 260 megawatts. So power conversion is available for those kinds of power levels. Not closed, open cycle only. Closed cycle is a big challenge still. So there are a lot of research opportunities. Mm-hmm. Yes.
So besides NASA, how many government agencies have to approve the moving and launch of the reactor, and how long will it take for all that paperwork to be filed?
Well, that's actually something it's a great question, and it's It depends a lot on work that is going on right now, today. There's a lot of focus on those questions because if we're going to beat China, we got to deal with that question, right? And so the agencies that need to approve it, of course, NASA, the FAA, which does commercial launch, the Department of Energy will have to. If it's an HEU system, the president actually has to sign off. I'm not exaggerating. If it's a HALEU reactor, that's not necessary. Again, because of the low enrichment levels that we're talking about. So the regulatory constraints are a big issue, and in fact, we talk about that a lot in the report that Cale mentioned. So the report we published last year. So if you're interested in that kind of challenge, there's some more information in that report. But it's getting a lot of attention because you're absolutely right. It's a huge issue. It is solvable, right? In fact, I helped write some of the latest nuclear launch approval process documents just in the background. It's important to be quantitative and not qualitative in your fears about launching nuclear. The other thing about launching is you launch a reactor having never operated it, so it's not radioactive. Reactors become radioactive after you turn them on. Before that, you can go up and hug it, right? You can. It's okay. It's safe. After you turn it on and run it, you can't. You die if you do that.
The implementation of these systems, it's going to be government. At what point do we expect it to transition into a commercial application?
It's a great question. So in our report that we published, we talked about the first time having it be 25% commercial, 75% government. And then over the course of 2 or 3 more systems, you would shift from primarily government to primarily commercial. And so by the 5th or 6th one, it would be a commercial enterprise. That depends on a market being created where people actually need that kind of power on the surface of the moon. And so there's really this bootstrapping process that you got to launch the first one, create some infrastructure, and then encourage people to come use the power, like I was describing earlier for the habitat and the rovers, some exploration, some exploitation, a little, start the process of bootstrapping a lunar economy. And then by the 3rd or 4th or 5th system, hopefully then there's enough of that kind of activity to warrant real commercial investment. I mean, these investments are not out of the world. Right now, the kind of investments that are happening in nuclear power system are far larger than what we're talking about. We're talking about billions of dollars for the first one. Probably 3 to 5 billion for the first one. After that, the cost comes down dramatically as you ramp up production. Okay, thank you all for putting up with me.
Thank you so much, Dr. Myers.